It's so special.
Yeah, IC 1396A. It's not just a pretty picture, though it is a spectacular one. It's like a giant lab for understanding how the biggest, baddest stars can actually kickstart the birth of new ones.
I've seen the pictures. It really does look like, an elephant's trunk reaching out.
It really does. And that shape tells us a lot. See, it's what astronomers call a bright rim cloud, a BRC. Think of it like a neon sign, The massive star's energy lights up the edge of the cloud, makes that rim.
So it's like a spotlight on this huge cloud of gas and dust.
Exactly. And with BRCs, what's really cool is that radiation, the intense stuff from nearby stars, it slams into all that gas and dust. That interaction, that's key to figuring out this whole triggered star formation thing.
And that's where we put on our detective hats, right? This paper used some pretty incredible telescopes, Chandra, Spitzer. They can see stuff we can only dream of.
Oh, for sure. Chandra, Spitzer, those are like our cosmic magnifying glasses. They cut through the dust, let us see what's really going on. One thing they help us figure out is a star's age, and that leads us to this big clue, the age gradient.
Okay, cosmic fingerprints. I like it. But how can you tell how old a star is?
Well, imagine a forest, right? Some trees are massive, ancient, and some are just saplings. You can tell roughly how old they are just by looking, right? The size, the bark. Astronomers, we do something similar with stars. We look at their light, their makeup, all sorts of clues.
So they did that with the stars in and around the Elephant Trunk Nebula.
They did, using all that data from the telescopes. And here's what they found. The stars, all clustered near that bright rim, the neon sign part, they're actually younger than the stars further in.
So it's like the cool kids hanging out closest to the action?
Exactly. The older stars are chilling further out, closer to what we call the Trumpler 37 cluster. Think of it as like the downtown of this region. It's old, about 4 million years on average. And it's home to the nebula's ionizing star, this real powerhouse called HD 206267.
So the youngest stars are hanging out with the biggest, baddest star around, and the older ones are keeping their distance. That age gradient, that's our smoking gun, isn't it?
Got it? That pattern tells us something big is going on, and that something is called radiation-driven implosion, or RDI. It's how this massive star is sparking the birth of all these new ones.
Okay, so HD 26267 is like the life of the party,
Yeah.
and all the young stars are clustering around it. But why? What exactly is RDI, and how does it work?
So picture this. HD 26267, it's like a cosmic blowtorch, right? And it's blasting out all this radiation and stellar wind, this intense energy just constantly hitting that surrounding cloud of gas and dust.
Kind of like a cosmic tanning bed, but instead of a tan, you get new stars.
Yeah, you could say that. And it's not just a light breeze either. We're talking intense pressure.
Yeah.
This bombardment, it compresses the gas in the cloud, squeezes it tighter and tighter.
Like a stress ball, but on a cosmic scale. All that squeezing has to have some kind of effect.
It does. It builds up and builds up all that density in these pockets of gas, and then boom, it's so dense that new stars ignite. The force of that massive star literally triggers their birth.
Talk about being born under pressure, but this isn't just a theory, is it? You said the researchers actually found evidence for RDI.
Oh yeah, we're not just speculating here.
Yeah.
They analyzed everything, the way the stars are spread out, how bright they are, tons of data.
They were really on the case, real cosmic detectives.
Totally. And they didn't just stop at, okay, we think RDI is happening. They went further and figured out how many stars in the region got their start, thanks to this one big star.
How many? Don't leave me hanging.
Somewhere between 14 and 25%. Almost a quarter of the stars in that whole area owe their lives to HT 26267.
That's wild. That one star is responsible for so many others.
It really shows you how important triggered star formation is. It's not just a fluke. It's a huge part of how the universe makes new stars.
It's mind-blowing. If all this is happening right now, imagine what it'll be like over the entire life of the nebula.
It's pretty incredible to think about. And remember, we're only seeing a tiny slice of time. This nebula and others like it, they're always changing, always moving. There's so much going on.
So we've got this star shaping the nebula, creating new stars with its energy. What else can this research tell us?
Well, it gives us a glimpse into how powerful stars really are. It's not just about shining brightly, it's about influencing everything around them, creating these stellar nurseries, changing how the whole region evolves.
It's like dropping a pebble in a pond. The ripples just keep going. This one star's energy is affecting everything around it, even millions of years in the future.
That's a great way to put it. And there's something else about HD 26267. It's not just making new stars, it's making the process Well, better.
Better? How so?
Usually with these giant gas clouds, the ones that birth stars, only a tiny bit of the gas actually becomes a star.
Yeah.
It's like having all the ingredients for a cake, but only making a couple of cupcakes.
Okay, I'm following you.
But here, in the Elephant Trunk Nebula, with this RDI thing happening, way more of the gas is getting used up, turned into stars. The efficiency is way higher.
So HD 206267 is like a super baker, getting way more bang for their buck.
Exactly. It all comes down to that squeezing, that compression from the RDI.
Mm.
It makes the gas denser, more likely to clump together and collapse, which is how you get a star.
So like instead of gently setting down the flour, you're giving it a good whack, making it denser.
Right. And that seems to be the key. HD 206267, it's not just throwing energy around, it's sculpting the environment, making it perfect for stars to form.
Amazing. But I bet there's still a lot we don't know about this whole process, right?
Oh, absolutely. We've just scratched the surface. Like, how does RDI really work? What's happening at the tiniest level? And how does it change depending on the star? Bigger star, more squeezing, things like that?
So many questions. And it makes you wonder, is the Elephant Trunk Nebula unique? Or is this RDI thing happening all over the universe?
That's the million-dollar question, isn't it? And that's why we keep looking, keep studying. Every time we find a new star-forming region, it's a chance to learn something new about how stars are born, how galaxies evolve, the whole shebang.
This whole deep dive has been incredible. Makes you realize how much is going on out there, how powerful just one star can be. I'll never look at the night sky the same way again.
That's what it's all about, right?
Yeah.
Realizing we're part of this vast universe with so much left to discover.
Well, on that note, I want to thank you so much for joining us for this amazing journey into the Elephant Trunk Nebula. Until next time, keep looking up and keep those cosmic questions coming.